Swayam Prabha. Digital India. Educated India.
Welcome to the lecture on hypothesis testing. In this lecture, we are going to test some of the hypotheses that we've earlier learned on a sample of data. Now, this data is the data from the predicting price of pre-owned cars. So, let's see how to read the data. Like I said, all hypotheses in this lecture are going to be checked on a sample of data. Now, we already have a sample1.csv with 1000 records. Now, this is a pre-sample data that is available to you, and this is the data set that we are going to read. And all hypotheses are going to be checked on this data. You need to use the function read.csv. Now within codes you need to give the name of the file with the extension. So sample1.csv is the name of the file along with the extension. Now once you run this command, it is read as a data frame and stored with the name sample. Now sample is the data frame and this is what we are going to be using for all the hypotheses. Now to check how many records or rows are there in our sample, I am going to use the command nrow, and within parentheses you just need to supply the name of the data frame. In this case it's sample. So nrow of sample basically returns the number of samples or the number of records or basically the number of rows in your data frame. I am saving it with the name sample underscore size, and that is the sample size that we have, and you can print your sample size here and it says 1000 records. So basically I have 1000 samples here. So this is how you find the sample size. So the first hypothesis that we are going to check is using the one sample test for mean. Now the hypothesis is as follows. It says 3 years back the average price of a used car was $6,000. Has it changed now? So this is your hypothesis. So let's see how to go about it. So what you see here is the steps involved in hypothesis testing. Now I am stating my hypothesis here. Now my null hypothesis denoted by H0 is given as mu is equal to 6000. So 6000 is your postulated mean. It is the mean that you want to check against. Now my alternate hypothesis states that the mean is not equal to 6000. So mu is used to denote the mean. So your sample statistics is basically x bar and s. X bar is the sample mean and s is the sample standard deviation. Because we are given only a sample here, we cannot comment on the standard deviation of the population, and hence to compute the test statistic t, we are going to be using the sample mean and the sample standard deviation. So the critical values is the next thing that you will have to enter. Now this is something that we have to find from the data. The test statistics, like I earlier said, is the t value. We are setting a maximum uncertainty as 0.05 and that is represented by alpha. And computed uncertainty is something that is computed after you run the function for one sample test for mean. So in hypothesis testing, you need to take a decision at the end based on all the parameters that we are going to be calculating. So after computing all these parameters, we need to take a decision on whether we are going to reject H0 in case we have sufficient evidence. In case of insufficient evidence, we are going to fail to reject H0. So that is the final decision that we are going to take. So let's move further and see how to compute these values. I'm going to first start by defining my postulated mean and see what my sample mean is. Now the postulated mean is 6000. So it is a mean against which you want to check. Now I'm saving it with the variable name POS underscore mean. So this is going to be the variable that holds the postulated mean. Now my sample mean is something that I derive from the sample. Since we are testing it for a column price, I am going to calculate the mean of this column, and the mean of this column turns out to be 6188.34. So this is the average price in your data, and this will be our sample mean. So let's see how to conduct the one sample test for mean. So to conduct one sample test for mean, you need to use the function t.test. Now there are several inputs that you have to supply to this function. The first is the column for which you are testing. Now here we are doing it for price, so I am just accessing from the data sample. So I am just giving it as sample $price. So the next parameter is mu, which is the postulated mean. We have already saved it as 6000 under the variable POS underscore mean. So this is the mean against which we are going to check. The next is confidence level. So confidence level is 1 minus alpha. Alpha is the significance level, and 1 minus that value gives you the confidence level. Our significance level is 0.05, and hence our confidence level is going to be 0.95, which is 1 minus alpha. Now we are checking for whether the mean is equal to 6000 or not equal to 6000. So that makes it a two-sided test, and hence alternative takes the value two-sided. So once you run this, I have the result saved under result underscore one sample. Upon printing it, you'll see a very well described output. It tells you first the name of the test, which is one sample t test. That is what we are conducting. Now under data, you will basically see the name of the variable that we have used. We have used price from sample. Now below that, you have the t value, the t statistic, and the value is 0.814. So that is the t statistic. The degrees of freedom is 1 minus the number of rows in your data, so it's 99. And p value is the computed uncertainty level, now which is equal to 0.415. It also states your alternate hypothesis, which means true mean is not equal to 6000. That is the alternate hypothesis. And it gives you the 95% confidence interval using this data, and it returns the sample estimate, which is the mean of price available in your data. To fill in the table from here, we are going to take the t statistic and the p value. We also need the critical values for filling in the table, for which we are going to use the degrees of freedom. But before we move further, let's just see how to calculate degrees of freedom. So to calculate degrees of freedom, I just need to get the number of rows. So you can either use the function n row or length. It returns the number of rows in your data frame. In this case, I'm just using length. So n is 1000. And to compute degrees of freedom, I just need to subtract 1 from the number of records I have, and that makes it 999. So I'm just printing the number of records and the degrees of freedom here. So we have assumed a level of significance of 0.05, that is 5%. So we are going to use the degrees of freedom and the significance level to compute our critical values. Now this is the only other value that we need to compute to fill in the table. So let's see how to compute the critical value. So to compute the critical value, we are going to be using the function qt. Now all critical values are obtained from the standard distribution. Now the distribution that we are using here is the t distribution, and that's because we are checking for one sample test for mean. The statistic used is a t statistic, and hence we are going to be using only t distribution to calculate our critical values. So this holds good for other kinds of hypotheses as well. So depending on the kind of hypothesis and the distribution that you are using, you're going to be deriving the critical values only from that particular distribution. So let's see how to compute the critical values here. So qt is the function, t is an abbreviation for t distribution, and q means quantiles. So you need to basically supply our significance levels here. Now because it's a two-tailed distribution, I'll be using alpha by 2 and 1 minus alpha by 2, and the degrees of freedom is what we've calculated earlier. And once you run this function, the critical values are stored as CV, and I'm just printing the critical values here. So you will see that the critical values are minus 1.96 and plus 1.96. So this is the critical value. So now let's go and see how does the table look with all these values. So I have not changed anything in the first two entries. I have the hypothesis as stated. We have the sample statistics that we've calculated. Now the sample statistic is 6188.34. Now that is the mean of price in your data. Now the test statistic that we computed was the t statistic with a value of 0.815, and the critical values turned out to be plus or minus 1.96. The maximum uncertainty was again fixed at 0.05, and the computed uncertainty turned out to be 0.415. Now depending on all these values, we need to come to a decision on whether we are going to reject null hypothesis or do we fail to reject null hypothesis. So let's take each of these values and let's check what is the decision that we are going to draw. There are two ways to come to a conclusion. You can either use the test statistic or you can use the p value. The test statistic is the t statistic and its value is 0.815. Now if this value lies within the critical value limit, then you basically don't have enough evidence to reject your H0, so you fail to reject H0. However, if it's outside this limit, the critical value limit, then you can reject H0. So the second way of arriving at a decision is using the p value. So to arrive at that decision, you're going to compare the p value with alpha, Now, if your p-value is less than alpha, then you can reject your null hypothesis. Otherwise, you fail to reject your null hypothesis. So, in this case, for the t-value, my t-value is 0.815. Now, it's well within this limit and my computed p-value is greater than alpha. So, both these values suggest that we don't have enough evidence to reject our null hypothesis, and hence our decision is going to be fail to reject null hypothesis. So, this is how you arrive at a decision given these values. So, let's check our next hypothesis, which is one sample test for proportion. So, 3 years back, the percentage of used car with automatic transmission were 23%. Now, my question now is, has it changed? This is our hypothesis and this is what we are going to check. So, I have the hypothesis testing steps listed here. So, we have the hypothesis as proportion equal to 0.23 or not equal to 0.23. P hat is a proportion that we have to calculate from the sample. My test statistic in this case is going to be the z value, and the critical values is what we have to compute. We are again setting the maximum uncertainty alpha as 0.05, and computed uncertainty has to be computed from the data, and then we will take a call on whether to reject H0 or we fail to reject H0. So, let's see how to go about it. We will be using again the same data frame, which is sample. So, since we need to compute the percentage of car with automatic transmission, we are going to be looking at the variable gearbox, which has two kinds of transmission. One is automatic and manual. Automatic is what we are interested in. So, I am just going to tabulate the frequencies of both of these categories, and you will see that there are also 15 blank cells, but we are not going to deal with them. So, here we are just going to extract the number of records with gearbox equal to automatic, and you can just get that from the table itself. So, I am just again getting the frequencies and I am just getting the second value. The second value is automatic equal to 214, and the reason I have again indexed it twice using a square index is because I don't need the level and the frequency, I just need the frequency alone. Okay. So, I am just saving it under count and I am just printing the value, which you will see is equal to 214. Now, the total number of observations that we have here is again 1000. So, I am just getting that from the records itself using the function length, and I am saving it as n observation, and my postulated or the hypothesized value that I have is P0, which is equal to 0.23. So, what we earlier saw was the frequency. Now, we are going to compute the proportion. So, for proportion, you just need to divide the sample frequency by the overall observations, by the total number of observations. Now, in this case, it's 1000. So, what you see here is basically the individual frequencies divided by the total number of observations. So, now we need to compute the z statistic because we are going to use one sample test for proportions. So, to compute the z statistic, you need p hat, p0 and sigma p. Sigma p is the error, n is n observations here, which is the total number of observations, and p0 is the hypothesized or the postulated value, which is 0.23. Now, p hat is the proportion that we've earlier calculated. P hat is 0.214. It's count by number of observations. So, since we are interested in the automatic gearbox, so we are just going to be taking the proportion of that. Standard error is nothing but P0 into 1 minus P0 divided by n observations, the square root of it, and P hat, like I said, is count divided by n observations. Now, that turns out to be 0.214. Okay. So, I have just printed the P hat value here, which is 0.214. Now, we are going to be computing the z statistic based on this formula. So, it's P hat minus P0 divided by the standard error, and your z statistic turns out to be minus 1.20. Now, since this is not an inbuilt function, we need to compute the p value from here and the critical value, right? So, your p value is going to be using the function p norm. Now, since this is a z statistic, it's from a standard normal distribution. So, hence we are going to be using the normal distribution to get the p value and as well as the critical values. So, to get the p value, you need to use the function p norm. The first parameter is q, which is going to be the z value that we've earlier calculated. I am giving the lower tail as true in one case and the lower tail as false. So, this is a two-sided test and there's an equal chance of that value lying in either sides. So, hence I am giving lower tail as true in one case and lower tail as false in one case, and in one case I am giving q as z and the other case would be q as minus z. So, this is how you calculate your p value. And to get your critical values, you are going to be using the function q norm. Now, q norm is used to get the critical values from a standard normal distribution, and you can just give your alpha by 2 and 1 minus alpha by 2 the significance levels, and this gets saved under the variable name CB underscore norm, and you will see once you print it, you will see that it's plus or minus 1.959. So these are your critical values. So let's just fill in the respective cells that we've earlier left empty. Now my postulated value is 0.23. This is also going to be my null hypothesis, and the alternate is it's not equal to 0.23. The sample statistic is p hat, which is 0.214. My test statistic is the z statistic, which is equal to minus 1.2, and my critical value is going to be plus or minus 1.96. My maximum uncertainty level is 0.05. So that has been already described earlier. My computed uncertainty value is 0.229. So since our test statistic lies well within the critical value limits and p value is greater than alpha, we do not have enough evidence to reject the null hypothesis, and therefore we conclude that pi is equal to 0.23. So let's go with the two sample test for means. So in this case, we would like to check if the mean price of cars that have run between 30,000 to 60,000 kilometers, now is that the same as that for the cars which have run 70,000 to 90,000 kilometers. So let's see how to go about it. So we have the hypothesis testing steps listed here. Now your hypothesis is going to be mu1 equal to mu2 and mu1 not equal to mu2. Now mu1 and mu2 are basically the means from both these groups. One is 30 to 60,000 and the other is 70 to 90,000. Now sample statistics is going to be x bar, like I earlier said, because we need to compute the average price for across both these groups, and instead of population deviation, since we've been given a sample, we are just going to be using the sample standard deviation. We have two kinds of test statistics here. So the first test that we need to do is an F test and then followed by a T test. So the F test is performed to check whether the two groups have equal or unequal variances, and then we do the T test. So similarly, you are also going to have two kinds of critical values and two values for the computed uncertainty. And based on that, we are going to take a call on the hypothesis that we earlier stated, and we are assuming a significance level of 0.05. So let's see how to go about it. So first we need to test whether the variance in the price of cars across both these groups are the same or not. But before we move further, we basically need to read the sample files. So you have been provided with two files. One has the records of all the cars which have run between 70,000 to 90,000 kilometers, and the other for all cars between 30,000 to 60,000 kilometers. Like the name of the file suggests, both these are samples. Now there are 500 samples in each of these files. One file is with cars which have run between 70 to 90,000 kilometers, and the other is for cars which have run between 30,000 to 60,000 kilometers. Now both these are samples, so there are 500 samples in each of the files. Now like the name suggests, these are samples. So from the original data, there was a condition to subset records which match 70,000 to 90,000 kilometers, and from that 500 records have been sampled, and the same thing has been done with the other case as well. So we can now read the file using the read.csv command, and I am saving them under the respective names. So once you run this, you will basically see sample underscore 70,000 underscore 90,000 in your environment, and also the same case with the other data frame. So first we need to compute the sample variance for price for both these data frames. So I am using the function where, and then we also compute the sample mean. I am using the function mean. So these are the two sample means that we have. So I am going to start by computing the F statistic. So I am just giving the ratio of the variances for both these records. So the first record is 70,000 to 90,000 kilometers, and the second record is 30,000 to 60,000 kilometers. And from each of these data frames, we are just accessing price. So the ratio of the variances is going to give us the F statistic, which is equal to 0.558. So let's calculate the degrees of freedom and the p value based on the F statistic, and we are going to compute the critical value from the F distribution. So to compute degrees of freedom, just subtract 1 from the length of the records, and we already know that we have 500 records under each of the data. So I'm just subtracting 1, that makes it 499 and 499 for both these records, right? So that's going to be my degrees of freedom. So using the degrees of freedom, we're going to compute the p value. So I'm going to use the function pf, f because it's from an F distribution. So the input to this function is basically q, df1 and df2. Q is the statistic, df1 and df2 are the degrees of freedom across both these data frames. So that turns out to be 5.05 into 10 power minus 11. We are going to compute the critical value from the standard F distribution. So we are using a function qf here. Now the inputs are basically going to be the significance levels. So since this is a two-tailed test, it's going to be alpha by 2 and 1 minus alpha by 2. I'm just going to supply the degrees of freedom that we've earlier computed. So your critical values are 0.84 and 1.19. So these are your two critical values. So your F statistic is basically outside this limit. So now that we have computed the degrees of freedom, p value and the critical value, let's decide whether the samples have equal or unequal variances. So the null hypothesis is that both the samples have equal variance, and the alternate hypothesis is that the samples have unequal variance. So the sample statistic is the variance that we earlier computed, and the test statistic is the F statistic, which is equal to 0.56. The critical values are 0.84 and 1.19. The maximum uncertainty, we've assumed it to be 0.05. Computed uncertainty is 5.05 into 10 power minus 11. The F statistic is outside the critical value limits. So the computed uncertainty, which is the p value, is less than alpha, and hence we are going to reject the null hypothesis, and therefore we are going to conclude that the variances are unequal. So let's use this information to conduct our two-sample test for mean. So for the unequal variances, we are going to use the Wells t-test for two sample. In the two-sample test, we are going to compare mu1 and mu2, which is the mean across both the groups. Now again, I'm going to use the sample mean and the sample standard deviation. So the test statistic is basically the Wells t-test statistic for unequal variance, and we also need to compute the critical value and the uncertainty. So again, I'm going to use the same t.test function. Now you need to give two inputs to this. So I'm giving the price from both these data frames, which is sample underscore 30,000 underscore 60,000 and sample underscore 70,000 underscore 90,000. The alternative is two-sided because we want to check whether they are equal or unequal. Confidence level is 0.95 because our assumed significance level is 0.05, and 1 minus that gives you the confidence level. I'm setting the parameter variance.equal to false because from the earlier F test we found that both the samples have unequal variances. So the reason of doing the F test was because we need to check whether the variances are equal or not, and that goes as an input to the parameter variance.equal, and depending on whatever decision you're drawing there, you just need to set this parameter as true or false. So in our case, the variances are unequal, so I'm setting it as false. So once you run this command, the results are saved under result underscore two-sample, and I'm just printing it. So you have a very well described output here. So you have the heading, which is Wells two-sample t-test. Now it gives you the input, which is the column price for both these data frames. My t value, which is the t statistic, is 7.28. My degrees of freedom is 923.7. and it says the p value is 7.26 into 10 power minus 13. Again, you get the alternate hypothesis, the confidence interval and the sample estimates. We have the t statistic and the p value to fill in the table, and let's use this degrees of freedom to arrive at critical values. But before we go further, let's understand how are the critical values obtained. So this is how the degrees of freedom is defined when you have unequal variances. Your S1 is basically the sample standard deviation of the first group. Your N1 is the corresponding number of samples, and your DF1 is the corresponding degrees of freedom for the first sample. Similarly, your S2 is basically the sample standard deviation of the second group, and N2 is the corresponding number of samples, and DF2 is the corresponding degrees of freedom. For us, the first data is 30,000 underscore 60,000 sample, and the second sample is basically the 70,000 underscore 90,000 samples. So these are based on the kilometers that we've earlier read. So now we need to compute N1 and N2, which is the number of samples across both these data frames. So S12 and S22 basically represents S1 square and S2 square. Whenever you have sample standard deviation square, it becomes the variance. So I'm just directly calculating the variance here. So let's now compute the degrees of freedom. So instead of having S1 square, I just have the variance square here, and similarly S14 will be variance square. So similarly for the others as well. Once you substitute the corresponding values in this term, you will get a value of degrees of freedom, which is equal to 923.70. Now then we are going to compute the critical value using this. For my critical value, I need my significance level. Again, it's a two-tailed test, so I'm giving it as alpha by 2 and 1 minus alpha by 2, and the degrees of freedom that we've earlier calculated. And I'm just giving these as input to the function qt, and this is your critical value limit. Now let's just plug in the corresponding values that we found in our table. So the test statistic is equal to 7.28, and the computed uncertainty is 7.26 into 10 power minus 13. Now the test statistic is outside the limits of the critical value, and the computed uncertainty, that is the p-value, is less than alpha. So both these evidence suggest that we can reject our null hypothesis. So we can conclude that our mu1 and mu2 are not equal. So this is how you go about a two-sample test for mean. So now let's do a two-sample test for proportion. Now here we are going to check if the proportion of petrol cars are they different across the time periods 2009 to 2013 and 2014 to 2018. So this is our hypothesis. So in order to go further, we are going to first list down the steps. Now I'm going to check if the proportions are same or not. So pi 1 is equal to pi 2 and pi 1 not equal to pi 2. So our sample statistic is going to be p hat. Now this p hat is a pooled estimate which is later used to compute the standard error. The test statistic is again going to be z value because we are computing it for proportions. We need to find the critical value and the p value, and we are going to assume an alpha level of 0.05. So now this is the formula that we have. So to compute p hat, which is a pooled estimate, you have the formula as n1 p1 plus n2 p2 divided by n1 plus n2. n1 and n2 are the number of records under each of these categories, and p1 and p2 are the corresponding proportions. So the standard error is given by this formula. Once we've computed our standard error, we can compute our z statistic. So now you've been given two sample files, and one for the year 2014 to 2018 and the other for the year 2009 to 2013. Now again, just like I earlier said for the previous example, we've taken the original data and from that we've placed these two conditions, and in both the subsetted records we've drawn 1000 sample each, and this has been provided to you in the form of a CSV file. You need to read these CSV files using the command read.csv. Once you read them, you can check the number of rows that are in each of these, and like I earlier said, you will find 1000 records under each of these data frames. Now what we are interested in knowing is basically the percentage of records which have fuel type as petrol. So the output that you see here basically gives you the frequency for all the categories under the column fuel type for both the data. For the year 2014 to 2018, 494 records have a fuel type as petrol, and for the other set of data you will find that 506 records have fuel type as petrol. So these are the two values that we are interested in, and I'm just going to use a condition to extract them and save them under count. So we are basically summing up all records where fuel type is petrol, and again here we are summing up all records which have fuel type as petrol for 2009 to 2013, and in this case we have 2014 to 2018. Now once you do this, I'm just concatenating the two counts using C, and I'm just saving them under count. You can see that we have the desired count value is here. So we know that count divided by the total number of observations gives you the proportion. So in the first case the proportion is 0.494 and in the second case it's 0.506. So my P1 is basically going to be 0.494, so it's the first count divided by the number of observations, and similarly my P2 is going to be 0.506, and N1 is going to be the number of observations in the first set of records, and N2 is going to be the number of observations in the second set of records. So we need these values to compute P hat, where P hat is defined as N1 P1 plus N2 P2 divided by N1 plus N2. So that is what we are going to do, and then we are going to compute the standard error S. So let's first compute the P hat, plug in the corresponding values in the formula, and you will get a P hat value of 0.5. Now then we are going to compute the standard error. So we are going to use the P hat value that we earlier computed and N1 and N2 and plug in all the corresponding values in this equation to arrive at a standard error value of 0.022, right? So these are the two values that we will need, and using this we are going to compute the Z statistic, which is nothing but P1 minus P2 divided by S, and that turns out to be equal to minus 0.536. So this is the value that we have. Now again we have only the Z statistic, so we need to compute the P value here and the critical values. So I'm using the function P norm. Again you need to give, so to compute P norm you need to first give Q equal to Z and lower tail as true in one case, and in the other case I'm giving Q equal to minus Z and your lower tail as false. So this is how you get your P value, and similarly like how we've earlier seen, your critical values are obtained using Q norm and I'm just giving the input as alpha by 2 and 1 minus alpha by 2 because it is a two-tailed test, and that turns out to be equal to plus or minus 1.96. So let's plug in the values in the table. I have the test statistic as a z statistic, which is minus 0.54. Now critical values are plus or minus 1.96. Z statistic is well within the limits, and you can also see that the computed uncertainty, that is the p-value, is greater than alpha. So therefore we don't have sufficient evidence to reject the null hypothesis, and hence the decision is going to be that we do not reject the null hypothesis. So therefore both the proportions are equal. So next we are going to test for chi-square test of independence. In this case, the hypothesis is that we want to check if the vehicle type is dependent on fuel type. So let's see how to conduct a chi-square test of independence. Now for this test alone, we are going to be using the entire data, which is cars_sample.csv, and I'm replacing all blanks with NA, right? You will see a lot of empty cells in your data, so I'm just replacing them with NA. So once you read your data, we need to subset based on a certain conditions. Now these conditions were used exactly what you've seen in the case study. So we will first start by building a cross table between fuel type and vehicle type. Now within the table function, we'll mention the fuel type which will go on the rows and the vehicle type which will go on the columns. Now under the parameter use NA, I'm going to mention it as no, because we don't want any of the NAs to be used to compute this cross table. So you see a gist of the cross table here below. So to conduct the chi-square test, I'm going to be using the function chi-square.test. So the input basically is the cross table or the contingency table that we've earlier built. So this is the reason of building a cross table, because that becomes the input to the chi-square.test function. Now once I execute it, I have the result saved under result underscore chi-square. So what you see here is the Pearson's chi-square test. The data that you get is the cross table or the contingency table. Your chi-squared value is 7987.7. Your degrees of freedom is 42. And your p-value is basically 2.2 into 10 power minus 16. So let's see how to arrive at these values. So your formula for chi-square is basically summation of observed values minus the expected value whole square divided by the expected value. So each of the expected value is basically calculated using this formula. The subscript I represents rows and j represents columns. So each of the expected value for each of the row and the column combination is calculated as Ri into Cj divided by n. Now n here is the total number of observations. So let's just do it for the first row and the first column. So the first row is basically the fuel type CNG and the first column is with bus. Now I'm just computing the row sum and the column sum. So the first row sum, the entire sum of the rows, so that's going to be 68, and the first column sum is 3545. So first row sum is basically sum of all frequencies under the first row, which is for CNG. Now the sum of first column is going to be the sum of all frequencies under the column bus. Okay. Now n is basically the total number of records, so that's going to be sum of all the elements in the cross table. So n is going to be basically the summation of all records in the cross table, and that's given as 38,825. So I'm just printing these values out. So your Eij, that is your I and your j for the very first element, which is a combination of CNG and bus in the cross table, is given by Ri into Cj by n. So which turns out to be equal to 6.208. Okay. This is the first expected value. The observed value is the frequency that you see in the cross table. So you need to subtract both of these, square them, and then divide it by this value and sum it across all rows and all columns to arrive at the chi-square. So this is how the chi-square is calculated. What I've shown you here is just one of the expected values as to how it's computed. So let's now look at how to compute the degrees of freedom. So to compute the degrees of freedom, I'm basically taking the number of rows and the number of columns from the cross table, and I'm just subtracting each of these by 1. So you have the number of rows minus 1 and the number of columns from the cross table minus 1. So that is 6 into 7. So what you see here is the value 42. So this is how you compute degrees of freedom. So to calculate the critical values, we are again going to be using the degrees of freedom and alpha. It's again a two-sided test. So we are going to be using alpha by 2 and 1 minus alpha by 2. So you see that the critical values are equal to 25.99 and 61.78. So this is the critical value. So now let's plug in all these values to arrive at a decision. So your chi-square statistic is equal to 7987.7. These are your critical values, and your uncertainty level is less than 2.2 into 10 power minus 16, right? So this is from the output. So here you can see that your chi-square statistic, it's outside the critical value, and your p-value, which is the computed uncertainty, is also lesser than your alpha value. So in both these, evidence suggests that we can reject the null hypothesis, and we can conclude that vehicle type is not dependent on fuel type. So to summarize, in this lecture, we saw how to conduct hypothesis test. We saw how to conduct a one sample and a two sample test for mean, and a one sample and a two sample test for proportion. And we also looked at how to conduct a test for independence. What we also learned was how to use test statistic p-value and critical values and arrive at a decision for your hypothesis testing. Thank you.